This is Brom Bresenham. I just finished week 6 of rebuilding Axor the Mighty in the Godot engine. It's been 3 weeks since my last weekly devlog, but it took me this long to create a new UI plugin for Godot that facilitates creating user interfaces that support dynamic layout, also known as responsive layout, that adjust and scale the user interface automatically as the screen size, or more importantly, the aspect ratio, changes. Technically, it took me 2 weeks to write the plugin, and then 1 more week to do the necessary art for the icons, write the documentation, and package it all up. The name of this Godot 4 plugin is GameGUI, and it's published on my GitHub. The address is shown on the screen. It's available for download and use in your own projects. I recreated my Axor user interface from scratch using the GameGUI plugin. Here's the result. While I don't have any logic to handle landscape mode window sizes, I'm very pleased with the results in portrait mode sizes. In this devlog, we'll go through the steps necessary to recreate this user interface using the GameGUI plugin. Here's a brand new project. I downloaded the latest release of the GameGUI library. Its add-ons folder is here in my temporary folder. I dragged the add-ons folder into the Godot project. I also drag in some assets from Axor that I'll need to recreate the user interface. I enable the GameGUI plugin from the project settings menu. I create my main game scene with a root node of type GG initial window size. All of the GameGUI nodes are prefixed with GG. The base node is called GG component, and then the others extend its functionality in some way. GG initial window size is a good root node for any scene because it sets the initial window size to be its own size, allowing us to easily test with different window sizes without going into project settings each time. A GG initial window size node only sets the window size if it is the root node of a scene, allowing it to be the root node of a child scene without disturbing the main scene. I set my main window size to 333 by 777 pixels. As I've mentioned in the past, I believe that's the narrowest aspect ratio currently available on devices, so I want to test that as one extreme. We'll add a child GG component and name it Arena View. To that, we'll add a color rect so we can see where it is. The GameGUI layout nodes can contain any regular control node. They treat any such non-GG control node as automatically expanding to fill available space. Let's create a GG VBox to give us a vertical layout. We'll use 2 more color rect nodes for a header and a footer, which will eventually become the status bar and action bar. Let's work towards giving the arena view its proper size. First, we'll change its horizontal and vertical scaling modes to fixed, and we'll set its fixed pixel size at 333 by 333. Now, we'll change its scaling mode to parameter and supply parameter names. A parameter is a dictionary setting, which we'll see more of in a moment. Those parameters aren't defined yet. Note that it falls back to the configured layout size when a parameter is undefined. We can set parameters in the editor by going to the root node of a GameGUI subtree and adding them to its parameters dictionary. More often, we'll want to set parameters via script as the display size changes. We add a GG layout config node as the first child of the scene root. That node's onBeginLayout method is called when the layout begins, so we'll extend its script and override that method. Be sure to give the script a tool annotation so that the script runs in the editor, not just at runtime. I've got the Axor Arena view logic typed out in a separate file, so I'll copy-paste that in. I went through this logic in a previous video, so I won't dwell on it here. Suffice it to say that onBeginLayout is called with the current display size, aka window size. I run some computations on it, and then call inherited method setParameter with various parameters I want to let other GameGUI nodes use. It's always a good idea to reload the current scene after you've added or modified a tool script. Now the Arena View component is dynamically sizing according to the design of the game. You may have noticed that the script saves a descriptive string parameter as well as pixel width and height parameters. Let's add a label to the Arena View to display that info parameter. We'll use a GG label instead of a regular label because a GG label can automatically scale the text as the size of the layout changes. First, we'll set the label to a test string just to get the font size and alignment correct. Notice the label doesn't yet automatically scale. To scale the label, first we need to assign a reference node. This is any parent node or node in a higher subtree, closer to the root, that the size of the label should vary proportionally with. Next, we set the label's text size mode from default to scale, and voila! Finally, let's set the label text to the saved parameter string. We'll need a small script to do this. Extend the ggLabel script and override the onUpdateSize method. Set the label text to getParameter quotes arena view info. The second argument is the default result if the parameter is undefined. Oh, I forgot to make it a tool script. Once I fix that, then we're in business. There's a static screenshot of the Axor Arena. Let's add that as a child of the Arena View node as a GG texture rect set to aspect fill, the default. A GG texture rect is just a texture rect that automatically configures some relevant properties once a texture is assigned to it. I'll turn on Arena View's Clip Children to hide the overflow. As a side note, I intended to move the Arena Dimensions label in front of this background image, but I forgot while recording this part of the video. Now let's create a separate scene to compose the status bar component. Let's start with a GG initial window size root, as usual. I'll use iPad dimensions as a design reference. iPad is the widest portrait mode device I need to support with a 3:4 aspect ratio. On a 768 by 1024 pixel iPad, the computed size of the Arena View leaves me with 324 extra vertical pixels, so I'll have the top status bar and the bottom action bar both be 768 by 162. Now, what I'm really talking about is aspect ratio. I'm saying that on the widest portrait mode device, the status bar aspect ratio will be 768 to 162. I could design this bar using pixel size 768 by 162, 384 by 81, 1536 by 324, or any other size that keeps the same aspect ratio. But 768 by 162 fits my screen nicely. I'll design at that size, and I'll also accommodate the status bar expanding vertically. For the background panel texture, we add a GG texture rect set to aspect fill. I'll set its vertical alignment to be shrink end to keep its bottom edge aligned with the bottom edge of the status bar. Before getting too far along, let's instantiate this child scene in the main game scene. Yep, looks good. There's a little transparent gap in the reference gameplay image, so I'll set my background color rect to black. Let's add a GGV box as another layer that contains the panel frame images. The original panel art is 1800 by 378, and I sliced it into its 4 edges. We'll use GGTextureRect nodes for the top and bottom of the frame, set to aspect fit. For the middle, we'll nest a GGH box and give it GGTextureRect nodes for the left and right edges. The middle component will be a GG filler, which is a regular GG component with a default name that makes it obvious that its job is to fill up excess space. Aspect fit won't look right here. Instead, let's set the height to expand to fill and the width to proportional. In proportional width, layout size X specifies a fraction of the available width to use. These edge pieces are 25 pixels wide, taken from art that is 1800 pixels wide. So we set the layout size X to be 25.0 divided by 1800.0. Bam! Let's make the bottom action bar scene, which uses different frame graphics. Same approach on everything. Okay, looks good. When the display has a very narrow aspect ratio, there's going to be a lot of unused panel space at the top and bottom. We could limit the panel height with an aspect fit node, but let's try something different here. Let's have the excess height at the top fade to black. To do that, we'll need a GGV box as another layer. It will have 2 children, a GGTextureRect with a fade from black gradient and a GG filler node. The fade texture will be expand to fill, and the filler will be set to aspect fit. Looks good. We could do the same thing for the bottom, but I'll move along to the next thing. Let's design one of the counters that goes on the status bar. There will be 3 total, called Rampage, Score, and Gold. Let's start with Rampage. Add a general GG component to hold the counter layers. Add a GGTextureRect as the background with this pennant image. Let's try another GGTextureRect with the Rampage icon, a skull. The problem is, it fills up the whole space, and we want to scale it smaller. For that purpose, make it the child of a GG overlay node. A GG overlay lets us position and scale the layout area available to children. It gives child content sprite-like positioning. Now, the GG overlay occupies the full width of the panel content area by default. Let's set its size to proportional mode. Its proportional size would be relative to its parent by default, but we can also assign a reference node, the pennant, and it will base its proportional size on that. So we want the overlay to be 100% of the size of the pennant reference node. Now we can position and scale the overlay content freely. Let's scale it down and slide it up a bit. We'll need another GG overlay to contain and position the GG label that will be the rampage value. The next issue is that the rampage counter is scaling with the entire panel. We want to constrain it to the lower part of the panel that never has any fade from black shading. An easy way to do that is to change the content hbox to maintain an aspect fit using the size of that area within the original art as the aspect ratio. The original frame is 1800 by 378. The sides are 25 pixels wide each. The top is 37 pixels high, and the bottom is 92 pixels high. We set the aspect ratio to 1800 minus 25 minus 25 by 378 minus 37 minus 92, and bam! Nope, wait, it's not sizing quite right. Let's set the width mode to expand to fill. Now only the height is constrained by the aspect ratio. There we go. Last thing for the rampage counter, let's set its subtree root size mode to be shrink to fit children so that it takes up the minimum amount of width. Let's make two copies of the rampage counter and adjust them to be score and gold counters. When we replace the texture on a GG texture, we can uncheck is configured, and it will reconfigure the node properties for the new texture. One caveat for copy-pasting the first counter is that the various reference nodes in the new counters refer back to the nodes in the original counter. This will still work, but if the original counter is deleted, then the other two will stop working until their reference nodes are adjusted. Here I adjust the label reference nodes, but for completeness we'd need to adjust the GG overlay proportional reference nodes as well. The game is looking good at 333 by 777 pixels, the thinnest portrait mode aspect ratio. I'll switch the initial size to 600 by 800 to match the widest portrait mode aspect ratio of the iPad. Looks good. There's one final thing. It's hard to notice here, but the icons and other textures don't look that great when they're scaled down, or in other words, on a low-resolution device. Notice how the dark edge of the star has gaps, and there are similar pixelation problems on the other icons. What happens is that while a standard linear filter blends together adjacent texture pixels as an image is scaled down, it can only blend together two horizontally adjacent source pixels at a time, and likewise two vertical pixels. So when an image is scaled below half its original size, gaps in pixel blending begin to appear. It's an easy fix. We just need to re-import our texture images with MIP maps enabled. MIP maps are pre-scaled smaller versions of the original texture that can be automatically swapped in when necessary. Step 1 is to select all the files we want to add MIP maps to, switch to the Import tab, check Generate MIP maps, and click Re-import. Step 2 is to select the root scene node and switch its texture filter to Linear Bitmap. Nodes inherit their parent's texture filter by default, so all other nodes in the scene will now use the Linear Bitmap texture filter as well. Let's make the change to the game scene root as well, and we're good to go. Alright, that's a wrap on week 6, and I'm excited to turn my attention back from plugin development to game dev. Catch you later.